be positive. And thank you very much. So here is Einstein a few years later, wishing he had never considered the possibility that in the vacuum the equation might be anything other than the Ricci tensor vanishes. And we'll come back to that equation a little bit later. But more generally, one can consider this more general condition that the Ricci curvature is a constant times the metric tensor. By the way, why do we call the metric tensor G? Anyone ever thought about that? It's actually Einstein's notation because for him, G was the gravitational field. So as punishment, because he considered this the worst blunder of his life, mathematicians call lambda the Einstein constant. And it has the same sign as the scalar curvature of the Einstein metric. The scalar curvature is the trace of the Ricci tensor. So the sign of the Einstein constant is the same as the sign of the Einstein. This Einstein constant and scalar curvature have the same sign. Scalar curvature is the dimension times the Einstein constant. And let me remind you that the scalar curvature, and not everyone uses this notation. This is a minority notation here. I use S for the scalar curvature. So again, if you look back at the Taylor expansion for the volume form I wrote down, and this has the very immediate meaning that it's actually asking, the sign of the scalar curvature is asking whether for a very, very tiny ball, a Riemannian ball of that radius would have larger or smaller volume than it would in Euclidean space. And moreover, there's a quantification of that which involves the ratio of the volume in the manifold versus that in Euclidean space involves the minus the scalar curvature times a dimensional constant as the second order term in the Taylor series expansion. All right, so this Einstein equation, or Einstein condition, generalizes the condition of constant sectional curvature, but it's considerably weaker. In dimensions 2 or 3, in fact, the Ricci tensor determines the entire curvature tensor. So in those dimensions, Einstein is the same as constant sectional curvature. But when you get to dimension 4 and in dimensions above, constant sectional curvature certainly always implies Einstein, but the converse fails starting in dimension 4. So locally, constant sectional curvature manifolds are locally like a standard model. If the sectional curvature is 1, it looks locally like the unit sphere. Whereas for Einstein metrics, starting in dimension 4, they are locally genuinely not trivial. They're not based on some model. So there's a different flavor of geometry than what happens in lower dimensions. Of course, if you think of this just as a PDE, it is at least a determined system of equations in the sense that for a fixed lambda, the number of unknowns, the metric, the coefficients of the metric, coefficients of the Ricci tensor have the same number of terms, so this is a determined system. But on the other hand, if you were to look at the number of independent components of the Riemann curvature tensor, that grows much faster. So the number of components of the metric and the Ricci tensor, those are just quadratic in the dimension, whereas the number of components of the Riemann curvature tensor is quartic in the dimension. And so there is this transition where as I mentioned, it's higher and higher, you know sort of less and less about the shape of the curvature tensor just from knowing the metric is Einstein. So the Einstein equations are not literally elliptic, but there's a natural gauge fixing because you have choices of coordinates. If you choose to only look at coordinate systems where the coordinates are harmonic functions with respect to the metric, then in fact the Ricci tensor looks like half the Laplacian of the metric term by term. plus lower order terms. And of course, I've abbreviated that lower order terms as lots because there are lots of them. So the basic question, which was first posed by Yamabe, was not in his published work, but he went around his department asking people this question: does every smooth, compact, simply connected N-manifold admit an Einstein metric? And the reason that he wanted to know this is if the answer was yes, then you would automatically have solved the Poincare conjecture. So he wanted to know if you had a manifold if you had a simply connected 3 manifold, if it had an Einstein metric, it wouldn't be very hard to show that, in fact, it had to be the standard 3-sphere. And in fact, the answer to Yamabe's question is definitely yes in dimension 2. That goes back to Riemann. In dimension 3, it really is one way of formulating the Poincare conjecture, and it actually is kind of the ancestor of the idea of the Ricci flow, tried to push a metric towards being more and more Einstein by a parabolic flow. And so we now know that the answer is yes in dimension 3. The answer to this question is yes. But in dimension 4, in the 1970s, Nigel Hitchen observed that the answer to this question is no. There are lots of simply connected 4 manifolds that do not admit Einstein metrics, and I'll show you why that's true in a minute. In high dimensions, this is really still very much open. In dimension 5, there's a good chance that the answer might be yes again. So there are amazing constructions just from Sasaki-Einstein geometry where you can produce, with some very minor topological constraints, you can produce Einstein metrics on a very large sector of simply connected 5 manifolds. But ultimately, we really don't have any idea what's going to happen in higher dimensions. So in dimension 3, as I mentioned, the Ricci flow is the key to answering the question of positive sense. And as I said before, in dimension 3, Einstein's equations are locally trivial. An Einstein metric on a 3-manifold has to have constant sectional curvature. And so the idea to prove the Poincare conjecture and more generally to geometrize 3 manifolds is to show that something like a 3-sphere would have to have an Einstein metric. On the other hand, it's not like every 3-manifold will carry Einstein metrics. So there is a very important obstruction. If a 3-manifold admits an Einstein metric, because its universal cover is a simply connected complete manifold of constant curvature, and so therefore either the sphere or it's contractible, the second homotopy group of the manifold has to be the same, because that's the same for the universal cover and for the manifold. And so when you have a 3-manifold which is a connect sum of 2 3-manifolds, it can't admit an Einstein metric unless it's a kind of trivial connect sum. So the connect sum, which we'll see many times in this lecture, is the operation. You take 2 manifolds of the same dimension. For simplicity, I'll imagine that they're both oriented, and then you cut a ball out of each one and you glue them on the boundaries in a way that's compatible with the given orientation. So this is a very familiar operation when you say, what's a surface of genus 2? It's a connect sum of two tori, right? And this generalizes to higher dimensions. It's called the connect sum. So so what happens in the Ricci flow is it's trying to push a metric to look more like an Einstein metric, and what happens is you develop necks where you have 2 spheres which are kind of shrinking down, and the Ricci flow is trying to pinch off these 2-sphere necks. So it turns out that every 3-manifold can be written as a connect sum of manifolds that are not themselves connect sums. This is called the prime decomposition. And there's one extra, well, there's one complication about it. You have to rule out S2 times S3. So there's a prime decomposition of 3 manifolds, and that just naturally falls out of the Ricci flow program. In dimension 5, the situation is very different. For example, if you look at Einstein metrics on the n-sphere, then starting in dimension 5, it's known that the n-sphere has lots and lots of Einstein metrics that are very different from the standard metric. So, for example, you can show that the moduli space of Einstein metrics on S5 has infinitely many connected components. This was first proved by Christoph Bloom, but later on Collins and Zekeri-Hidi gave a very different proof of the same theorem using Sasaki-Einstein geometry. So when I talk about the moduli space of Einstein metrics, I'm saying take the set of all Einstein metrics on the manifold and mod out by self-diffeomorphisms of the manifold, the diffeomorphism group, and also, to keep things simple, let's also mod out by constant rescaling. If you multiply an Einstein metric by a constant, it's still an Einstein metric. It changes the value of the Einstein constant. It multiplies by the inverse of the constant you multiply. But so we don't want to think of those as somehow different, right? Those are cheap, free solutions you get out of one solution. Given one Einstein metric, you can move it by diffeomorphism, you can rescale it. Those are all the same point in the moduli space. So for example, you can show that any connect sum of S2 times S3s admits Einstein metrics, and that the moduli spaces are always highly disconnected. And basically, most simply connected spin factor 5 manifolds also admit Einstein metrics by the same kind of construction. So you could look at the work of Boyer and Galiski and Goulart just to see how this is proved. So dimension 4 is the topic of my lecture, and the situation is encouragingly different. So in high dimensions, if you're trying to say, let's understand the topology by find an Einstein metric on the manifold, you can't tell if it's the sphere or not by looking at an Einstein metric. Right? You get out your microscope, you look at a little piece of an Einstein metric on the sphere, you wouldn't know it's a sphere. But in dimension 4, there are all kinds of positive results available that show us that there's some relationship between Einstein metrics and topology. So in the 60s, Marcel Berger showed that any Einstein metric on the 4 torus is flat. And this is a non-trivial theorem in the case when the Einstein constant is negative. So here I'm saying, the Einstein constant is allowed to be anything you like. It's saying that the only Einstein constant possible on the 4 torus is the Einstein constant 0, and the metric is actually flat. So in particular, that says the moduli space of Einstein metrics on the 4 torus, is connected. The only choice is that you're looking at Euclidean space modulo some lattice. So there's a choice of the lattice, but that's a connected set of choices. There's another manifold I'll talk about in a few minutes called K3 in dimension 4. And Nigel Hitchen proved in the mid-1970s that any Einstein metric on K3 is Ricci flat and Taylor. It's what's now known as a Calabi-Yau metric. Actually, Yau didn't prove the existence of Einstein metrics on K3 until about 3 years later. But already it was known by Hitchen that if you had an Einstein metric on K3, it would be a Ricci flat Taylor metric. So I'll talk about K3 a little bit later. K3 was named by Henri V. It stands for Kummer, Taylor, and Kodaira, who were the 3 pioneers of the subject. Kummer going back to the 19th century. They always had this peculiar sense of humor. And when he named it K3, he said it was named for these 3 people and the beautiful mountain K2 in Kashmir, which had just been climbed for the first time. And so the implication was that K3 was going to be a harder climb than K2. So it turns out that after hard work by a number of people, you can show the moduli space of Einstein metrics on K3 is actually connected using this observation of Hitchen, using Hitchen's theorem. So the next piece of encouraging news was proved in 1994 by Besson, Courtois, and Gallo, and they showed that if you had a compact quotient if you have a manifold whose universal cover, it admits a constant curvature metric, its universal cover is hyperbolic for space. Well, the hyperbolic metric, the standard hyperbolic metric is an Einstein metric, and the theorem is that's the only Einstein metric on a hyperbolic four-manifold up to diffeomorphism of rescaling. And a few months after I found out about their theorem, using a very different set of techniques, Seiberg-Witten theory, I was able to show that if you had a compact quotient of complex hyperbolic space, so this arises as a complex manifold, you're looking at the unit ball in C2 modulo a group of bipolymorphisms such that the quotient is compact and smooth. There turns out to be huge numbers of these. There's an infinite hierarchy of them. Then on such a manifold, the only Einstein metric is the obvious one, the complex hyperbolic metric. This is a symmetric space metric, modulo diffeomorphisms and rescalings. All right, so these are examples where the Einstein condition in dimension 4 still has some of the flavor of what one sees in dimension 3, that the geometry is closely tied to the differential topology. So 4 dimensions is exceptional, and I like to think of it as a Goldilocks zone for Einstein metrics. People that grew up in the English-speaking world will know what I mean by the Goldilocks zone. This is stolen in current, so it's not too, the Einstein condition leads to metrics. It's not too rigid, it's not too flexible, it's just right. And so if you didn't grow up with this particular folk tale, it's the story of Goldilocks who goes into a house that's owned by 3 bears, a family of bears, and tries out their beds and tries out their soup and so forth. And it's always, this one is too soft, this one is too hard, this one is just right. And but the use of this in scientific context, the most common use of the Goldilocks zone is for people that are studying exoplanets. When you're trying to imagine a planet around another star that might have life on it, you don't want it to be too hot, you don't want it to be too cold, you want it to be just right? That's the Goldilocks zone, or the habitable zone. All right, so for the study of Einstein metrics, dimension 4 really seems to be the Goldilocks zone. The equation's genuinely non-trivial, and yet there's a lot of rigidity left over, which is reminiscent of low-dimensional phenomena. Now, one of the interesting things that comes out of this, and I will not have the time to talk about this today in any detail, it turns out that the existence of Einstein metrics on a 4-manifold actually depends upon the diffeomorphism type and not the homeomorphism type. So for example, K3 has infinitely many different smooth structures. There's only one smooth structure for which there's an Einstein metric. There are topological 4-manifolds which admit an Einstein metric for one smooth structure, but not for most others. And so if I were giving a different lecture, I might make that the subject, but I just don't have the time. But the main idea is that while most 4-manifolds do not admit Einstein metrics, the same thing happened in 3 dimensions. And what happened was there was a decomposition. The Ricci flow decomposed 3 manifolds into pieces which were geometric, and one might hope that there's some similar story in dimension 4. This is wide open. So the main point is that there's enough rigidity in dimension 4 that one can hope that if you have an Einstein metric, it tells you something about the topology of the manifold. Whereas in higher dimensions, it just turns out that Einstein metrics are too common. Dimension 4 is kind of the last dimension in which you could imagine there being some sort of geometrization. So what is so special about dimension 4? It's really a very peculiar dimension, and it's related to the fact that the rotation group SO4 is not a simple Lie group. Lie algebra is not a simple Lie algebra. It decomposes as a direct sum of the 2 subalgebras SO3, and those arise from the fact that the quaternion multiplied by the quaternions, which form the unit three-sphere, you can multiply either by on the left or by the right on the quaternions, thought of as R4, and those are different types of rotation. So this shows up. An infinitesimal rotation is a skew matrix. Another place in geometry where you see skew matrices are when you consider the coefficients of two forms. So this actually ends up saying that there's a natural decomposition of two forms into two three-dimensional subspaces. There's the two forms at a point are six-dimensional, but they break up as a sum of two different three-dimensional subspaces. Those are exactly the eigenspaces of the Hodge star operator acting on two forms. When you have a decomposition of two forms, that gives you a way of decomposing the curvature tensor, because you can think of the curvature tensor as a linear map from two forms to two forms. And when you have, by decomposing two forms into these more primitive pieces, you have a kind of block matrix decomposition of the curvature tensor. There's a piece of the curvature tensor that maps self-dual two forms to self-dual two forms. There's a part that maps the anti-self-dual two forms to self-dual two forms, and so forth. And actually, so this is the Bianchi identities tell you that this curvature operator map from two forms to two forms is actually self-adjoint. So this is a symmetric matrix. These look like two different blocks, but they're really just the transposes of each other. This is the trace-free piece of the Ricci tensor. And here the scalar curvature appears as the coefficient, as multiples of the identity, but then you also have other blocks. You can take the trace-free pieces of both of these blocks. So that decomposes the curvature tensor into scalar curvature, trace-free Ricci tensor, self-dual Weil curvature, anti-self-dual Weil curvature, where these last two pieces are actually conformally invariant. They're essentially unchanged if you multiply the metric by any function. So actually, one thing that falls out of this observation is that a four-manifold is Einstein if and only if its curvature operator commutes with the star operator. The star operator here looks like the plus the identity in this block minus the identity in this block. So to commute with that ends up saying that the trace-free Ricci tensor has to vanish, and that has the following cute but useless consequence. When you want to understand when is an Einstein, when is a four-manifold Einstein, it's the same as saying that there's a sectional curvature associated to every two plane, right? For an Einstein manifold, every two plane, well, in dimension 4, the orthogonal complement of a two plane is a two plane, right? As you see by tilting your head a little bit. So the Einstein condition is the same as saying the sectional curvature of the plane P is the same as the sectional curvature of its orthogonal complement. Okay, so that does give you some picture in your head about what does the Einstein condition mean, but it's actually not a terribly useful condition. So if you have a compact-oriented four-manifold, a more dramatic way of thinking about this decomposition is if you try to express the Gauss-Bonnet theorem in four dimensions. So there's a generalization of Gauss-Bonnet in any even dimension. It would say in dimension 4 that the Euler characteristic is gotten by integrating a certain quadratic expression in the curvature tensor, and it has to be invariant under change of frame. There's the kinds of terms you can get are the scalar curvature squared, self-dual Weil curvature squared, anti-self-dual Weil curvature squared, and trace-free Ricci curvature squared, and coefficients happen to work out like this. This is actually expressing the Pfaffian of the curvature tensor in a very concrete way. And you might notice here that it's only the trace-free Ricci curvature that makes a negative contribution to the Euler characteristic. So Berger used this in the 1960s to observe that a compact Einstein four-manifold has non-negative Euler characteristic, and if the Euler characteristic is 0, then actually the metric has to be flat. That was why I said before, the four torus, the only Einstein metrics on it are the flat ones. It comes out of this Gauss-Bonnet formula. But there's also another interesting invariant in dimension 4 that can be expressed as the integral of a quadratic integrand in the curvature, and that's the signature of the manifold. So the signature is the difference between two numbers b plus and b minus, and I'll explain what those are in a moment, but Tom's contribution was to observe that this signature is actually a multiple of the first Pontryagin number of the manifold, and the first Pontryagin number can be expressed in terms of the curvature of any connection on the tangent bundle. You do this for the Riemann connection. That's the formula you get. Tom did not literally write down this formula, but he was implicit in his result. This is often called the Tom-Hirzebruch signature formula. Actually, Hirzebruch didn't do anything in dimension 4. What he did was once he found out about Tom's result, he realized it could be generalized to dimension 4K. There's a signature of such a manifold, and it's expressible in terms of Pontryagin numbers. So these numbers b plus and b minus are defined in terms of the intersection pairing. So if there's a symmetric quadratic, there's a bilinear pairing on the second de Rham cohomology, which is you take two de Rham classes wedged together, representatives, and integrate, and that is in real cohomology, that really is the same as what's the cut product on H2. So you over R, you can diagonalize such a thing. And so it has a certain number of, in a suitable basis, it's expressed as plus the identity on one block and minus the identity on the other block. Those dimensions are b plus and b minus. They're actually, b plus is the maximum dimension of a subspace on which this intersection pairing is positive definite. B minus is the maximum dimension of a subspace of the second cohomology in which it's negative. So the difference between those two numbers is called the signature. All right, so when you put together those integral formulas, you get an amazing observation due to Hitchin from his paper in the mid-70s that twice the order characters plus 3 times the signature has this kind of expression where you don't see any contributions from the anti-self-Dual tensor, and where the only negative contributor is the trace-free Ricci tensor. So this characteristic number of the manifold would have to be non-negative if there was an Einstein metric. And actually, Hitchin went on to observe more. By the way, he discovered this combination just by playing with the integral formulas, but actually this number, 2 chi plus 3 tau, is actually the first Pontryagin number of the bundle lambda plus over the Four-Manifold. So it's not an arbitrary combination. So in fact, it turns out when you split up the curvature tensor into 2 columns here, the left-hand column is actually the curvature of the bundle lambda plus, and the right-hand column is the curvature of lambda minus with respect to the Riemannian connection. So if this number was 0 and you had an Einstein metric, what you'd find was that lambda plus was actually a flat bundle. And so this gives rise to, first of all, Hitchin showed that 2 chi plus 3 tau would have to be non-negative if you had an Einstein metric, and if you have an Einstein metric on a manifold where this number is 0, then it's a locally hyperkähler metric. I should say that it's very easy to write down simply connected Four-Manifolds, simply connected oriented Four-Manifolds for which this invariant is negative. So that shows that there are lots and lots of simply connected Four-Manifolds that don't have Einstein metrics. So this last condition about being locally hyperkähler is the same that lambda plus is flat. And then beautiful, rather long argument by Hitchin showed that actually that happens if only in the case when the universal cover, not the universal cover, a finite cover of the manifold is either the 4 torus or K3. So I just used some words: hyperkähler, Kähler, Calabi-Yau, Maybe many of you in the audience know what those words mean, but for those that don't, the right point of view is that these are statements about the holonomy of the manifold. If you choose an Riemannian manifold, connected Riemannian manifold, choose a base point, and then you can look at parallel transport around any piecewise smooth loop, and that gives you an orthogonal transformation of tangent space at the base point, which depends on the loop. It turns out that the set of all of the transformations that you get in this way forms a subgroup of the orthogonal group. For example, if you follow a given loop backwards, you get the inverse transformation. If you follow one loop by another, these holonomial transformations can decompose. So there's a holonomy subgroup of the orthogonal transformations of tangent space, and by choosing a suitable orthonormal basis, you can just say that's a subgroup of ON. Now, if the dimension is even, one possible subgroup is that you can have the standard representation of the unitary group acting on CM. So remember that the unitary group is by definition the intersection of the orthogonal group with the complex linear transformation. So complex linear transformation is also an orthogonal transformation. It's called the unitary transformation. In fact, though, to say that if the holonomy is in the smaller group of SUM, the unitary transformations with complex determinant of an element of the circle, with determinant equal to 1, it's automatically the unitary group an element of the circle. But if it's actually 1, that's the subgroup SUM. And if the holonomy is in SUM, the manifold turns out to be Ricci flat Kähler. But in fact, if the manifold is simply connected, this is an exact equivalence. So a holonomy SUM on a simply connected manifold is exactly the same that you have a Ricci flat Kähler metric on it. And the ones with that property that the holonomy is actually SUM are called Calabi-Yau manifolds. So Calabi framed the Calabi conjecture about existence and gave a partial proof, and Yau did the part he was not capable of doing. All right, so, but there's another class of manifolds, the so-called hyperkähler manifolds are the ones with holonomy as an SPK, where SPK is the group of orthogonal transformations on the quaternions that are both also, let's say, right quaternionic linear. It's a subgroup of the special unitary group. But it's actually, you can think of it as a subgroup of the special unitary group in many different ways. You can think of I or J or K as the thing that you normally would call I and the square root of -1, right? So there are many different square roots of -1 of the quaternions. So Calabi introduced the terminology, it's a hyperkähler for manifolds where the holonomy is an SPK. All right, so in SP1 is in fact just a different word for SU2, just a different term for SU2, for the same group as the 3-sphere as a Lie group. And so in dimension 4, to say a manifold's hyperkähler is the same as saying that it's Calabi-Yau. So for a simply connected four manifold, hyperkähler is exactly the same as saying it's a Ricci flat Kähler metric. Okay, so I've been I've defined Kähler metrics in terms of holonomy, but that's not the way that they were invented, and people didn't make that connection for a long time. They were originally, so it turns out that these are exactly manifolds that have an almost complex structure, tensor, which is parallel with respect to the metric, and which is also adapted to the metric insofar as it acts by orthogonal transformations over tangent space. And when you have such a metric, then you also get an associated closed 2 form, such that the metric is determined by this closed 2 form. So in particular, Kähler metrics, there is a preferred element of de Rham cohomology called the Kähler class. Now, that's not the way Kähler invented Kähler metrics. He had no idea what he was doing. He did something that was crazy and stupid, but brilliant. His idea was that you should look at metrics where the components are given by the complex Hessian of a function. Why? Well, he did the computation. He found out that the Ricci tensors for such metrics had the same shape. That's what he did. All right, but it turned out Hodge then realized this was exactly what we needed in algebraic geometry, and things went on from there. The associated two form in that case is again just written in terms of the mixed partial derivatives of this potential function, local potential function, with respect to z and z bar variables. So, but again, the modern, I mean, that's a very strange thing. It's not a geometric definition. The geometric definition is that they are the metrics of where the holonomy is in the unitary group, or where the holonomy is complex linear for every group. All right, so one thing you get for free on any Kähler manifold is you get a non-degenerate two form, and that makes the manifold into what's called a symplectic manifold. So in particular, if you look at symplectic four manifolds, those are just four manifolds equipped with a closed differential two form, which is non-degenerate. So it defines an isomorphism between the tangent space and the cotangent space. So it's a classical Darboux theorem that there are always coordinates in which any symplectic form takes on the standard shape and given dimension. So dimension 4, it would be dx wedge dy plus dz wedge dt. If you have a symplectic structure, you can always choose coordinates in which omega takes that form. Of course, if you're on a Kähler manifold, those coordinates are typically very different from the complex coordinates. In Euclidean space, you could take them almost be the same, basically would be the real and imaginary parts of complex coordinates, but on a general Kähler manifold, the Darboux coordinates are different from the complex coordinates. So in particular, you might notice that there's a preferred orientation. You take the wedge product square of the symplectic form, and it gives you a volume form. And so when I'm talking about symplectic four manifolds, I'm always assuming that the symplectic structure, we're always talking relative to the orientation determined by the symplectic structure. Now, looking at symplectic four manifolds is an amazing laboratory for exploring Einstein metrics. Because Kähler geometry is a rich source of examples. And on the other hand, it turns out that in dimension 4, unlike in higher dimensions, there are constraints on the differential topology that come out of having a symplectic structure. It turns out that if B plus of the manifold is at least 2, then there's a non-trivial Seiberg-Witten invariant. I won't talk about Seiberg-Witten in this lecture, but it gives rise to non-trivial lower bounds for certain curvature functions. All right, so there's a certain level on which you can imitate aspects of Kähler geometry, even when dealing with non-Kähler metrics, if the manifold admits a symplectic structure. All right, so without going into how the details of how this is really done, here's some suggested questions. Suppose you have a four manifold that admits a symplectic structure. And then you could ask, can it also admit an Einstein metric where the Einstein metric doesn't know the symplectic form? They are like two people in a big city. They live in the same huge building. They've never met each other. They've never been in the elevator together, but they live in the same place. On this manifold, you imagine there is a symplectic structure and there's an Einstein metric. Does this tell us, does this lead to any non-trivial results? Well, it turns out that yes, they're very strong results. If we also require that the Einstein constant is non-negative, it turns out we can completely classify the possibilities of the diffeomorphism. So here's a theorem I published in 2009. Suppose you have a smooth, compact-oriented four manifold which admits a symplectic structure. And then it will admit an Einstein metric with lambda greater than or equal to 0, which is a priori completely unrelated to the symplectic structure, if and only if the manifold appears on the following list of diffeomorphism types. So if the diffeomorphism of the manifold can be a connected sum of CP2s and CP2 bars, where the number of CP2 bars is 0 to 8. And here, so CP2 bar means CP2 with the non-standard orientation, the one that doesn't come from this complex structure, and connected sum we saw before. The next possibility is going to be S2 times S2. Then it can be K3. I mentioned K3 before. Just to say a little bit more about K3, it arises as a simply connected complex surface, complex manifold of complex dimension 2 with vanishing first Chern class. It turns out that Kadairo's work showed that these are all the same up to deformation. Therefore, there's only one diffeotype called K3. If you're thinking of these as compact complex surfaces, there's a family of them, but there's only one diffeotype. So the typical model is to take a smooth quartic hypersurface in CP3. Kummer's contribution to the story was that he observed that, first of all, if you took a 4 torus and modded out by the sort of standard Z2 action, which is reflection on each S1 factor, then there's a diffeomorphism that can be realized as a singular quartic in K3. What he actually showed was that if you took T4 to be the card torus of a genus 2 surface, and then you could actually embed that quotient as a singular complex surface in CP3. And now it's a quartic, and you can now smooth the quartic by changing the coefficients of the equation, and the generic quartic in CP3 is a K3 surface. Magically interesting Four-Manifold, but the basic model is to take a smooth degree 4 complex hypersurface in CP3. So the theorem of first proposed by Calabi and then proved by Yao is that K3 doesn't Ricci 5K metrics. All right, so on this list, things that have symplectic structures and admit Einstein metrics with non-negative Einstein constant. We've seen these connected sums of CP2s and CP2 bars, S2 times S2. K3, it turns out that K3 has a non-trivial Z2 quotient called the Enrique surface. There's the 4 torus, and then there are various quotients of the 4 torus by Z2, whereas all arising as complex surfaces where these quotients are called hyperelliptic surfaces. So in terms of existence, you need the result here of Yao, some work of Qian, construction by a physicist named Page, and then a theorem I proved with Shushang Chen and Brian Weber. In terms of the fact there are no other things that belong on this list. Part of this comes from Hitchin-Thorpe inequality, but the lion's share is cybergrid theory. All right, so there are extensive results that come from similar techniques in the case when lambda is negative, but I can't possibly fit that in today. And if you want to ask me about that some time during the school, I'd be happy to point out some references. All right, so these are things that actually all arise as complex surfaces. Del Pezzo surfaces, K3 surfaces, Enrique surfaces, abelian surfaces, hyperelliptic surfaces. The first 2 lines here are called the Del Pezzo surfaces. Del Pezzo surfaces are, by definition, compact complex surfaces for which C1 is a Kähler class. It's not actually the Kähler class of, it's not really the relevant class for all of the metrics involved. The shorthand is very confusing for students is that people will say these are complex surfaces with C1 positive. C1 is a cohomology class. What does it mean to be positive? It means that it has a representative, which is a Kähler. So these are actually arise as complex surfaces, blow-ups of CP2 at K distinct points in general position. We have at most 8 points, or CP1 times CP1. So for example, if you have 3 points, they're not supposed to be collinear. Blowing up is the process where you can replace a point in a complex surface by a CP1, and where the normal bundle of that CP1 will be the Chern class -1 line bundle, tautological line bundle of CP1. The model is that the tautological line bundle is actually a sub-bundle of the rank 2 trivial bundle. And that gives rise to a map from that O-1 line bundle to C2, which just collapses the origin to a point. And once you have that model, you can then blow it, you can then glue it into a manifold. Just glue that picture. Think of a little neighborhood as in C2, you can glue that picture. All right, so in terms of diffeotype, the way that changes diffeotype is taking connected sum with the CP2 bar. So anyway, there's the moduli space, complex moduli space of these delta surfaces is very nice. For some reason, oops, I must have hit the button that says do not touch. Okay, so let's get back to it. All right, so the general position is that no 3 are on the line, no 6 of the blow-up points are on a conic, no 8 are on the nodal cubic with 1 point at the node. So the theorem is that every del Pezzo complex surface has a J-compatible conformally Kähler Einstein metric, and this metric is unique up to complex automorphism and constant rescaling. In other words, it's geometrically unique. Now, when I say conformally Kähler, this is not a Kähler metric. It's a Kähler metric multiplied by a pseudo function. So such metrics are still Hermitian, and it turns out that Hermitian Einstein metrics are always conformally Kähler in real dimension 4, not higher dimensions. So it turns out, in fact, this conformal rescaling is not an arbitrary function. It actually is expressed in terms of the scalar curvature, the Kähler metric. This Kähler metric is not an arbitrary Kähler metric either. It is a so-called extremal Kähler metric in the sense of Calabi. And so our existence proof depended upon the theory of extremal Kähler metrics. The first example on connected sum of CP2 and CP2 bar, a physicist named Don Page, who was a student of Stephen Hawking, wrote down by hand an Einstein metric on that manifold. He didn't know what the manifold was. He didn't know it was conformally Kähler or anything like that. And in fact, he actually tried to describe the topology of the manifold. It was misstated. Some people say this is on connected sum of 2 copies of CP2. They have different orientations. Derjinsky in 1983 then discovered that Page's metric was conformally Kähler, and it was conformal to an extremal Kähler metric, but later observed that this was actually an extremal Kähler metric that Calabi wrote down around the same time. There was work of Hsu and then by Tian and Yao to get Einstein metrics on most del Pezzo surfaces. Tian's famous paper where people attribute the result to Tian, turns out it has huge numbers of mistakes. And Tian was aware of the mistakes, but he never got a student to correct them. So there is a correct version of this proof that was finally written down. Very beautiful paper, Odaka, Spotty, and Son. I highly recommend it. It didn't come out until 2016. But the result that Tian claimed is correct. And then in the meantime, with Xusheng Chen and Brian Weber, we've handled the case of CP2 blown up at 2 points where there is no Kähler Einstein metric, but there is a conformal Kähler Einstein metric. In terms of uniqueness, there's uniqueness there by Bondo and Mabuchi, which I then was able to generalize to the conformally Kähler case in 2012. All right, so one of the fundamental open problems is to understand all metrics on del Pezzo surfaces. And the question is the Einstein moduli space connected? This is an open problem. I can't tell you the answer, but there's been a lot of progress. We have an open characterization of the known Einstein metrics on these manifolds. And my favorite I had one characterization that Peng Wu came along with a better criterion. It's a really beautiful idea. Look, you think of W plus as a map from lambda plus to lambda plus. So endomorphism of the self-doing 2 forms. And so that has a determinant. And Wu's criterion is to demand that the determinant of that map be positive. It's related to the fact that these metrics are all conformal to positive scalar curvature extremal Kähler metrics. That for the known metrics, this is satisfied, but this is an open condition. So Wu wrote one paper which I couldn't really understand very well, but I came up with a substantially different proof the same year. But he should get the credit because it was his idea.
if you have a compact oriented four-manifold, it's important to stipulate it's simply connected. And suppose that the self-dual Lau curvature has positive determinant at every point of the manifold, then in fact the manifold is diffeomorphic to a del Pezzo surface, and the metric that you're looking at is one of the metrics I discussed. So a simplified version of my argument is to say that because W plus has zero trace, determinant of W plus positive ends up saying it has a kind of Lorentz form. There's a unique positive eigenvalue, and then there are two negative eigenvalues. And when you look at the eigen subspace of lambda plus, that's a smooth real line bundle on the four-manifold. And now what you can do is the following weird-looking thing. If alpha is the eigenvalue, the positive eigenvalue, multiply the metric by alpha to the 2/3, and then choose an eigenform for it where the length is constant for that self-dual 2 form. And then by a long Weizenbach formula calculation, one gets the following amazing inequality that at every point of the manifold, 0 is greater than or equal to the covariant derivative squared of this 2 form with respect to this rescaled metric, plus something that smells positive but isn't pointwise positive. It's the inner product of omega with its Hodge-Laplacian. And if you're on a compact manifold, what you can now do is integrate. That's less than or equal to 0. The covariant derivative of omega has to be positive. It has to be 0. Therefore, that is a Kähler metric, a special holonym. All right, so that's the basic idea. So the corollary is that every simply connected or oriented Einstein four-manifold with determinant W plus is actually diffeomorphic to a del Pezzo surface. And the moduli space of all of those Einstein metrics exactly sweeps out one connected component of the Einstein moduli space. We know one connected component completely. Question is, are there other connected components? You need some new ideas. So here I've been focusing on compact Einstein manifolds, but we could also look at non-compact complete solutions of the Einstein equations, and those turn out to be very important through singularity by concentration singularity analysis. These turn out to be very important in the theory of compact Einstein manifolds too. So the terminology in this subject is that a gravitational instanton is a complete, non-compact, non-flat, Ricci flat Riemannian four-manifold. And here, notice that the Ricci tensor is 0. Einstein is happy again. It's unhappy because these aren't Lorentz metrics, they're Riemannian metrics. Nonetheless, this terminology smells like physics, doesn't it? I mean, gravitational instanton, this is the terminology introduced by Gibbons and Hawking in the late 1970s when they were at the top of their game. One example that you can write down immediately, if you know the form of the Lorentzian Schwarzschild metric external black hole solution, what you can do is, like analytic continuation, just change the sign of dt squared. And so you can write down, here's a Riemannian solution. This is a Ricci flat Riemannian four-manifold. Actually, Q point, it's actually conformal to, rho squared, there's the radius coordinate squared, and it's normalized so that the area of that two sphere is 4 pi rho squared. But if you divide by rho squared here, you get some metric on a two-manifold plus the standard two-sphere. Well, any two-manifold with an orientation is a Kähler manifold. This is conformally Kähler. So, and in fact, some general nonsense says this has to be an extremal Kähler metric in the sense of Coulomb. This metric here is actually extremal Kähler on R2. An extremal Kähler metric is one where when you take the gradient of the scalar curvature, you think of it as a 1-0 vector field. That's a holomorphic vector field. So Hawking observed that actually for this metric, you can view what was originally the time parameter, think of it as an angle. It's 4m times theta. And then if you introduce, make a slight change in the radius function, this becomes actually a Ricci flat Kähler metric on R2 times S2. And so its shape is that we've now made stuff involving R and theta look like Euclidean metric plus higher order terms, and then that's then there is a factor that in the S2 direction. It becomes this Kähler metric that I referred to is now a Kähler metric on C times CP1, and the Einstein metric here, if you take a slice of R times S2 and R2 times S2, you get this usual picture of the Schwarzschild neck. It's been rotated now to put in an extra angular variable. Another example is the Taub-Nut metric, which comes up as a non-trivial Einstein metric on R4. Here, this formula for it is not terribly enlightening. Really, the way that it's most usefully thought of. Here, it's displayed as a Hermitian but non-Kähler metric on C2. But it turns out that for the opposite orientation, it's actually hyper-Kähler. It's not Kähler for this orientation, but there is a kind of mirror way of looking at it. We change the orientation, and it actually becomes a hyper-Kähler metric on C2. So both of these examples are Hermitian and toric. Toric being the two torus acts isometrically on them. They're also asymptotically locally flat. That means that they approach a certain kind of model at a certain rate. But the thing that to most briefly understand what ALF means, it doesn't refer to the puppet character alpha. It's ALF is asymptotically locally flat. And it means the volume of a very large Riemannian ball doesn't grow at rate r, radius to the fourth, you would expect, but rather by radius cubed. All right, so my collaborators, Olivier Picard and Paul Gaudichon, showed in 2023, last year, that if you have actually this one paper was published, they proved it a little bit earlier, a smooth, complete, non-flat, Ricci flat four-manifold. So it's one of these gravitational instantons. You assume that it's toric, that it's ALF, so particularly it has this cubic volume growth, and that it's Hermitian with respect to some integrable complex structure. They were actually able to classify such things. So Hermitian, of course, means just that there, with respect to the integrable complex structure, J is acting by rotation at each point. You assume the metric's not Kähler, because there are lots of Kähler examples, and that would make the list infinitely long. But if you put in these conditions, then there's only a very small number of solutions. You get the top reverse-oriented Taub-Nut metric. There's another metric, diffeomorphic. The manifold is diffeomorphic to CP2 minus a point, called the Taub-Bolt metric, and it's actually Hermitian with respect to both orientations. There's a one-parameter family called the curve family that generalizes the Schwarzschild solutions. These are all Einstein metrics on S2 times R2. And then there was a surprise family found in 2011 by two guys in Singapore, Chen and Teo. At first, a lot of physicists didn't want to believe that these existed. These had nothing to do with analytic continuation for the Lorentzian metric. But it turns out that, so those are diffeomorphic to CP2 minus the standard circle. So I'm essentially out of time, so let me quickly get to the end. So these are all Hermitian, but in dimension 4, it turns out that a Hermitian Einstein metric is always conformally Kähler. This does not work in higher dimensions. It's absolutely false, starting in complex dimension 3. It also turns out that if you have a Kähler metric which is conformal to an Einstein metric, it is automatically extremal in the sense of Pallavi. And it also automatically admits a killing field. Turns out the conformal factor is always related to the scalar curvature of the Kähler metric. All right, so this is all very nice, but toric, they're saying you have killing fields. That's a highly non-generic condition. Hermitian, why would there be a complex structure? So these are interesting, this is a very interesting theorem, a beautiful theorem with a beautiful, complicated proof. And the proof is amazingly constructive too. So for example, they reproved the existence of the chain of tail metrics. But my observation was that actually these all satisfy the Ping-Wu condition criterion. Once you look at this proof in the compact case and generalize it to the non-compact case. And so what we proved together was that if you have one of the metrics on their list, and now look at another Ricci flat metric on it, which is C31 close to it. So that means that it's in a weighted norm involving the Riemannian radius. So demand that the difference between the two metrics, it's not just that it's C3 close, but actually the norm involves a weight of the Riemannian distance from a point. So the difference falls off like 1 over the radius. This covariant derivative falls off like 1 over the radius squared, and so forth up to the third derivative. Okay? So in a suitable norm, you take another Ricci flat metric, which is close to this known gravitational metric. Then, in fact, the new Ricci flat metric is another one of the metrics in their families. So this is a rigidity result. You don't get out of. So somehow there's a cozy little neighborhood of these Einstein metrics where you don't get other Ricci flat metrics. And so actually for this is an optimal statement of the result. You will not find in our paper. You have to put in an extra result due to student of Song Sun, Mingyang Li. This is a very fine contribution that came out around the same time as our paper. All right, so muchísimas gracias por la invitación. Estoy muy feliz de estar aquí. And I'm looking forward to returning to the Alhambra. So I hope that you're enjoying this conference as much as I am. I'm very happy to be here. I'll stop there.
Get this list of spaces that have both a reflective structure and Einstein metric. The Einstein constant is negative.
Right.
If you say it's positive, then some of these.
Yes. So then, in fact, we that result cuts it down to just the Del-Pezzo surfaces, and that's in my paper with Chen and Weber. So the first two lines of that classification were the Del-Pezzo surfaces, the connected sums of CP2s and CP2 bars to a certain number, up to 8 CP2 bars maximum, and S2 times S2. Those are the only possibilities. So the key point is that very few symplectic manifolds can admit a positive scalar curvature metric. So that cuts it down the list immediately, and then you apply the Hitchens-Brooke inequality, and then it's more delicate to include the zero case.
You mentioned that the tau metric on R4 is essentially another Einstein metric on the Euclidean space, which is not flat.
Yes.
Do you think the same should happen in S4 to produce another Einstein metric?
I don't know. That's a very good question. So when I was mentioning that there's a lot of rigidity in dimension 4, if you take a manifold that admits a constant sectional curvature metric, and if that the sectional curvature is 0 or negative, you find out that actually, you understand all of the other Einstein metrics on those spaces. They're all constant curvature. We do not have such a theorem for S4, and it's completely open. And hoping that the answer will turn out that the metric, the only Einstein metric on S4 is the round metric, but that may just be a primitive prejudice on my part. Go try to find one. It would be fantastic. Or prove that another one cannot exist. Techniques that are available in the positive case are surprisingly weak compared to. There was a general prejudice in differential geometry in the first half of the 20th century that positive curvature is easy and negative curvature is hard. Because when you're trying to, it took people a long time to realize that you could, for example, the Four-Manifolds theorem that produces lots and lots of negative Einstein constant compact Einstein four-manifolds by looking at Kähler-Einstein with Einstein constant negative. It turns out the Kähler-Einstein condition is easier when the constant is negative. The Yamabe problem is easier when the constant is negative, and so this old prejudice is just people were writing down things that had a lot of symmetry, and those don't exist. They don't have killing fields on negative Einstein metrics, right? But actually, there are many. There's a sense where, in terms of proving existence and uniqueness, things are better when lambda is negative. And I'm sorry I wasn't able to tell you anything about lambda negative today, but I only had an hour. And I'm going to talk about it once.
Other questions?
So you said that 4D is like the Goldilocks zone for Einstein. So the question is if every dimension is the Goldilocks zone for some equation.
Well, yeah, so that's an interesting question. It's sort of a mathematical question, sort of find the right question, right? I would be surprised if the answer was yes, but who do I know? How would I know? Great questions. Certainly go think about it. But so there are interesting generalizations of the Einstein condition. It turns out that many of them turn out to be surprisingly complicated compared to the Einstein condition. But that doesn't mean they're not worth studying.
Going to 4K, would that be a huge step, or is it believe that
Well,
can be managed?
So dimension 4K has some nice structures in it. I mentioned there's a so-called Hitchin-Thorpe inequality. Thorpe, who was actually a colleague of mine at Stony Brook when I first arrived, he went off and became, he ran a national teaching program afterwards. But his paper in the late 60s, he was working in dimension 4K, and he said, let's look at metrics that have the following curious symmetry property and blah, blah, blah. And he proved a certain inequality of characteristic numbers, which turns out not to be terribly useful. But then Berger pointed out that, well, in dimension 4, your condition is that it's an Einstein metric. So it's a footnote in his paper that it's a result. A corollary is a result on Four-Manifolds. So I mean, you can do things in higher dimensions. Higher dimensions are really wonderful for studying metrics of special holonomy. There are really interesting Ricci flat manifolds, Einstein manifolds in higher dimensions, which have other special holonomy groups. But what happens usually is that when you drop these special holonomy metrics into the sea of all Riemannian metrics, it's like they drown. They just disappear without, it's like you dropped a stone in the ocean, they just disappear. Whereas in dimension 4, it turns out that the fact that the special orthogonal group is not a simple Lie group ends up saying that there are things in common between general Riemannian metrics and metrics of special holonomy. So in particular, if a manifold has a symplectic structure, or more generally has non-trivial Seiberg-Whitman invariants, there are some tricks from Kähler geometry which do sort of survive. You get things that are equalities in Kähler geometry often become inequalities for general Riemannian metrics if there's some invariant as well. So somehow high dimensions are wonderful, and for studying Einstein metrics of special holonomy, huge progress has been made in recent years. But my own guess is that it'll turn out, we don't know very much about Einstein metrics of general holonomy in high dimensions. My guess is that they exist in amazing profusion, and that the special holonomy world is just a very tiny sector.
Now let's spend